at present you are using batteries, and that most of the batteries are lithium batteries. So first thing, environment concern is there, or health concern, and second thing, maintenance. So battery life is usually for 12 months, and with time its performance keeps on decreasing. We need to replace it frequently. Accessibility, it's very difficult to go to the faraway places and replace batteries frequently. Like it may be like if you want to track some animals in forest, now they want to keep track of most of the animals. They're using batteries. So once battery is dead, now it's very difficult to track those animals. Like how we go and replace that battery. So then this energy harvesting might come handy there. So we can tap the energy from motion of the animal, and you can supply that to the tracker. So a lot of applications, there are a lot of areas we'll discuss in detail about this application and real, like what are the different products available in market now that we'll discuss. So this is what I was talking about. This is how our battery operates. This is along X we have our time, and this is performance of the battery. As time goes, we can see that battery performance will decrease. And here we have this harvester, wireless sensor network running based on the harvester. We can see that frequently it keeps on charging, like at all the times. There is nothing like it doesn't have any peak performance there as compared to battery, but it keeps on working for longer period and it keeps on charging itself. So coming, like we are talking a lot about energy harvesting, power generation. It's not a new thing for most of us. We know wind energy, thermal energy, all are available. Like in what context we are talking about this energy harvesting? So we know this wind turbines, thermal, hydro generators, all those things. Usually they are used for mass production. It's the energy is in terms of mega scale, megawatt. And also we have second category which we say meso scale. For example, our gensets. So they can generate energy in terms of watts. But what we are talking today is about this micro scale. Okay? So we are generating energy in terms of ultrawatt to milliwatts. Maximum is 1 milliwatt. So that is what we are producing. But comparably, the size of harvester also will be smaller. So you can see the size of this generators here, and this size will be smaller. So these harvesters can be integrated along with sensor on your, you can say PCB or whatever. And this is how like miniaturization of our IoT is helpful for us. Like so these two things, we cannot think of using these two sources of power for IoT system. They are not feasible at all, and this is the only option that we can use for IoT system. So based on harvest, like we have seen, there are various options available. Like we have solar, thermal, all those things. So photovoltaic from solar, we can have energy output in terms of micro to milliwatt. From vibration also we have almost similar range. Thermal we have in terms of microwatts, and radio frequency it's little bit on lower side. So again, like we cannot say which is best and which is not suitable. Like it depends on the situation. Depends on where you are using for. For bridges, vibration is the best source. Though you are getting solar out there, but it has limitation. Like it is not available throughout the day or throughout the year. So, but on bridges, vibration is always there. When your vehicle moves, vibration is available there. It depends, depending on application, we can use one of these conversion technique. So this is what, like why we want energy harvesting, that we had a basic concept like why energy harvesting is required. And so what is the context, like it's not in terms of milliwatt or watt, it will be in terms of just microwatt and ultrawatt up to 1 milliwatt. So then we'll see what are the different mechanisms available, and what we are doing now here in maybe in India in particular, or in our college, what others are doing in other parts of the India, other parts of other countries. So let us start with thermoelectric energy harvester. Like all of you have studied in your physics, Seebeck effect, right? So you can generate a temperature difference with voltage input, So there is something like thermoelectric TEG, we call thermoelectric generators. So you have two sources, one is heat sink and heat source. There is a temperature difference. We have PN junctions here. So you will be using reverse effect here. We are not giving input as voltage and we don't want output as heat or temperature. Reverse, like we will be using temperature as input and reverse, like it will generate the voltage. So input is temperature here. We'll have two different junctions here. One is hot junction and we can say cold junction. Sink is cold, this is hot. So due to this temperature difference, there will be EMF generated or voltage generated. So this can be used for certain applications. We have certain wristwatches now which works on like the temperature on our skin and temperature in air will be different. Will keep on sweating. There will be variation in the temperature. So we have wristwatch. It has a temperature difference. So due to that, it can generate some voltage and it can be used for those smartwatches. So coming on to the vibration energy harvesting, actually we are working in our college. We work on this vibration energy harvesting as well as thermoelectric. In vibration, so once we have the vibrating source, like we have a lot of like as I took the example of vehicle or bridge. So source is available, so that can be converted into energy using one of these. Like, there are a lot of options available. So three main generators are electromagnetic, piezoelectric, and electrostatic. They'll be stored and used later. So we know most of these basic concepts. Like if you start with electromagnetic first, so you know this Faraday's law. So whenever a magnet moves in coil, so EMF will be generated. So based on the same principle, but so these all these more DC motors, all those things like this turbines, hydro generators, they work on same thing. Even wind turbines work on same principle. But here we'll be using smaller device. It will not be similar to any of these turbines. You can see here the size. So you have this AA size battery or harvester will be of almost of the same size, which can give comparatively similar output as this battery can give, but for the longer period. It doesn't have any life actually. This battery, I think you cannot use for more than a year. You have to replace after a year. So whenever with this is small device, one of first year student, he tested this. Like he did what he did is you can also do this in your do it yourself like home. You can take some small syringe, used syringes, and you can take some copper wire and magnets. You can put a magnet inside that syringe and put uh, this coil around the syringe, and you can test. If you vibrate it, if you shake it, you'll get some voltage output. This is how this electromagnetic energy harvesting works. So these are some mathematical equations. If you are well versed with your physics vibrations, we have inertia and damping as well as stiffness force. So this will be force vibration, and this is some coupled equation, electrical and mechanical, electromechanical equation. And you know this Faraday's law. Whenever there is a change in velocity, so due to that velocity, because of number of turns, flux, and inductance or length of coil, so you'll have the voltage produced. Whenever this moves, this magnet moves here, or this is a magnet or coil here. So whenever there is a relative motion between magnet and coil, so EMF will be generated. This is how electromagnetic harvester works. Now we have a special material called as piezoelectric. We all have learned this. This is a special material. We call it as smart material. What is smart? It has more than one function. It can do more than one function. You can see here. So what you are seeing is whenever you apply pressure on this piezoelectric material, it can generate a voltage here. So it has both properties, like as we discussed previously, TEG, thermoelectric generator. It can work in both a way. You can give mechanical input and you'll get electrical energy as output, or you can supply electrical energy as input, which will get the mechanical deflection as the output. So there in a thermoelectric, it is different. There it is heat and current. If you give the heat input, you'll get the voltage or current as output, you can give the voltage as input, you'll get the heat as the output. Similarly, this piezoelectric has in terms of deflection. So you'll be using the first principle where we'll give the deflection as mechanical deflection as input and voltage will be generated. A simple thing you can imagine a simple scale, or we can say cantilever beam, or you can take scale, we'll attach some piezoelectric here and we'll just shake it, so it will produce energy. Again, we have some mathematical relations here, so that if anybody interested, I can share with you some of the details to you. So each, as we discussed previously, that each of these methods or these transaction methods, they have their own advantages and disadvantages. Again, it depends on where you're using and what is our requirement. Usually, electromagnetic they'll be used when have a lot of space. It requires a lot of, like, it is large displacement device. You need a lot of displacement to take place in order to harvest the useful voltage or current. So whereas piezoelectric is smart, very small, in very small area you can have the energy harvested, and it can be useful where you have the space restrictions. And electrostatic, it needs some initial voltage. So that's a problem here. But it's not a smart material, it doesn't require any smart, like, so piezoelectric is little bit costlier compared to these two. Electromagnetic, you need just magnet and coil, but piezoelectric, we are not using directly piezoelectric device material, so we'll be using some composites, microfiber composites, which will be costing us more. Okay, again we'll go back to physics. Like, you might have heard of, you're aware of resonance. What is definition of resonance? So we know that there are two things. One is forced vibration or forcing frequency, or second is natural frequency. All of you know everything around us, every mechanical or whatever, every particle or every device has its own natural frequency. So if you take just a spring mass system, it is root over k by m. It depends on its stiffness and mass. It has its own natural frequency. When this natural frequency matches with this forcing frequency, example, here you have spring and mass, which are its own natural frequency, and the support is excited at that particular frequency. You can see initially when the support is excited at lower frequency, it is not matching, like you can see there is just rigid motion and there is no relative motion of this spring. Now you can see, so amplitude of this spring mass is increasing. Now you can, now frequency of both support excitation as well as spring mass natural frequency, they matched at this point, and that is resonance. At this point we will have the maximum amplitude of the spring mass system, and this is the limitation. Like, if you are dealing with linear harvesters, so our limitation is that we can get maximum power only at the resonance condition. That means your harvester frequency should match with the source frequency. For example, you have the source, or you want to harvest energy from the bridge vibration. So bridge vibration frequency should be matched with the frequency of the harvester you are designing. But the problem is that if you just deviate from this, from just 2 to 3% deviation from this resonance, if you are not attaining exactly resonance, you are just 5% falling behind resonance. If you are here, you can see there is huge drop in the power generated. That we say it has a lesser narrow band. You can generate only power only for particular frequency. You cannot harvest power for larger or wide range of frequency. There is a limitation of linear harvester. So there are some solutions that have been addressed. We'll discuss those solutions now. So we're coming, like, we have dealt with what linear harvester is and what are those limitations, how to come over that. So one option is, okay, why should we use only one harvester? So I said just one beam and one PJT. So why not we go for multiple harvesters? Like you can see here, this is one harvester 1, 2, it is harvester number n. But you can see that each harvester has different length. They are not of same size. If length is changing, that means its natural frequency is changing. So from harvester 1, you generate this much of power at this frequency. Harvester 2, you can have the power generated at different frequency. Similarly, for n harvesters, we'll have the power generated at different frequencies. Thereby, what we can do is we can cover a range of frequency. Even there is a deviation between our source like bridge and harvester, okay, we can cover like whatever frequency bridge is vibrating, let it vibrate. At any point, we are able to harvest this minimum amount of energy. This is one of the option, but what is the problem? You have to use multiple harvesters that demands a lot of space. But if you don't have any problem with space, you can go for this multiple harvester, no issue. Similarly, there are different things like instead of increasing length, we can keep on adding the mass also, n mass, change the n mass. And like from Barcelona, University of Brescia, they developed like small level, like MEMS level, they etch this kind of harvester. It is done by using etching process. Other option is, okay, what we can see here is there are two magnets at the bottom and a magnet at the end of this particular beam. You can see it is vibrating for larger frequency. So we call it as nonlinear harvesters. This is known by the famous scientist who gave this particular concept, bistable system, so it is known as Duffing. So it is known by his name, Duffing oscillator. What happens here is, in this case, it will have the maximum amplitude even if it is not at the resonance. So because of this, we can have, so we can see that like this particular beam is oscillating between these two magnets. Now sometimes only at one particular magnet at here. So it has two stable points. Usually stable point should be at the center and single stable point. Instead of that, we are introducing two stable points. So this keeps oscillating between two stable points for larger frequency. So by this, we are able to increase the bandwidth. So other nowadays a lot of things like I don't know how many of, okay. So we are talking about metastructures or metamaterials now. Maybe if you're watching commercials in TVs, some notebook or advertisement is coming like origami papers. All of us, we played during our childhood when we were kids. We used to make planes using paper. What you're doing in that paper, like you're making a plane out of single paper. There was no attachments, no staples, no pins, nothing, no joints at all. In a single paper, just by folding paper in artificial manner in such a way that it becomes a plane, that it becomes a board. So you take a single paper without any joint, we can have thousands of combinations. Like one Japanese professor, a scientist, is very expert in origami materials. You can search what is origami. Now we have kirigami also. So these are things which, like, you're not adding anything there. Like if you heard of composite materials, composite means it is mixture of two different materials, that is composite. But here, so that will change the entire property of material. Carbon fibers, this is a carbon and fiber, so it's a composite. So you are adding different materials to achieve that, like lightweight and high strength carbon fiber, but that is a composite. But without doing that, just making some changes in the geometry. So here you're not making any changes in composition point of view, it is just geometric change. So we call them as metastructure or metamaterials. They are artificially engineered materials. So you can see here. So what difference you can see? Like you have a lot of holes here. That's it. But so here these holes, if you observe carefully, they're not circular holes. First thing, they are a little bit elliptical. So it has major axis here, but one hole here, it has major axis on horizontal line. These small holes have major axis on vertical line. This what changes it can bring. What is happening here is actually if you take just a rubber eraser you are using, you just compress it, you press it. What happens? That rubber length will decrease, but whereas width will be increasing. Somewhere it has to compensate. Length decreases, width increases. That's what I think you might have studied, Poisson's ratio. But what happens here is because of there are different holes in different axes, so that change you cannot see. Length will decrease, whereas width will remain as it is. That this is beauty of metamaterials. You have different ways. So now here you can see Poisson's ratio will be negative. You might not have heard about Poisson's ratio being negative. Poisson's ratio will be usually 0.3 or 0.2 with positive. So with this you can play a lot of things. You can do a lot of things with this. Like it's not. It has applications in a lot of like maybe in particularly in aerospace. Okay? Without making any joints or making any addition of materials, you can play with the material property. That's by changing the geometry. You take simple paper. So if you hand hold the paper, it will not stand. Example, if I take this paper, it will not stay on straight. Right. So what you do is just hold it and then open it. So it will have some strength because of only foldings. What it did, we just changed the geometry of the paper. So it gained the strength without adding any material. So these metamaterials are now being used for energy harvesting also, so that you can improve the energy harvesting capability. These are the options available to overcome the limitation which a linear harvester has. Okay, now we come to the application. Like we have talked a lot about these harvesters, all those things, IoT. So where exactly are used? What is a market here? So this market survey has been taken from energy harvesting market from US party which has done this market survey in 2017. According to them, in 2017 there was a market transaction of $1.5 billion in different areas. It has application in different areas, mainly in consumer electronics. We'll see what consumer electronics it has application. It is covering $900 million. It may be military, aerospace application in terms of healthcare. Your smartwatches or wristwatches, industrial. So we are talking about IIoT, industrial Internet of Things. So these are all possible, and this energy harvesting has application in those areas. So now coming to real-time application, like where exactly? So still in research phase. They are not into the market. You can see a just wristband here. So it has some piezoelectric material inside it, okay, with small PCB also. So whenever your wrist makes movements, that movement will be converted into electrical signals. That signal again it acts as some sensors or diodes will be used. It will be acting as harvester as well as sensor. Okay, so these are the boards with sensor and harvester. Like so, all of us when we were kids of 1 year old or when we started walking, our parents gave us some shoes which has some lights in it. When you start walking, it makes some noise or it will illuminate an LED light. Okay, same method, but here is not just for illuminating light. It can power up to some sensor. There will be a lot of sensors here. It has specific application in military applications. It will give the energy to the sensors, and that sensor data can be used. So nowadays, some MIT, US, and some scientists in Southampton University, they are coming out with fabrics. These fabrics will have piezo wire in between. This is all textile. In between, you have piezo fiber inserted into it. So these fabrics, when you wear, so this will generate energy. Also, your backpack. Although we are using backpacks when you are going for trekking. So when you are going for trekking, like always, you need to charge your mobile. Okay. So even though you are using power bank, all those things, one option is whenever you are walking, so that walking can be converted into useful energy, and that can be used for charging your mobile. So backpack, we have a lot of options available to harvest energy from the backpacks. So you can see these are the piezo layers. Not only piezo, you can use also electromagnetic. So in medical field, like you might be knowing, you might heard of pacemakers. Okay, so pacemakers to power up them instead of batteries, we can use this harvester, which can make use of human body motion and heartbeats. It can keep on charging the pacemaker. And also we have some, like I said, we have something like bandage type sensors. This is similar to bandage with harvester and sensors integrated on it. Okay. What it does is it pulse rate. It will measure the pulse rate and send it to the system. or it will send the details to the doctor. Also, like nowadays, it has a lot of application. Like we are hearing about prosthetics. Many people like they are losing their legs, so they have to go with artificial legs. But artificial legs are a lot of problem. Like they have a lot of issues when wearing lot of artificial legs. They have itching problem, all those things. So for them nowadays, artificial legs are coming with some lot of sensors. So those sensors, we can power those sensors by using the energy generated during the walking. So recently, one of BTech students, they did survey on, so at different walking speed, how much energy is available and how much. So how to convert that? Like they found that they can harvest useful energy out of that, which can be used for the sensors. They did mostly they worked on numerical part, and so they are like next batch will work on experimental part. Now this day to day uses, you have remote. So Philips remote already into the market. So wireless remote sensor, so it completely operates on energy harvester. There is no battery or no space for battery. Instead of battery, there is a harvester. Like I was explaining, like why struck bridge. Nowadays, how a bridge maintenance takes place, how they do it. So at present, in India, most of the bridges are maintained by some agency. What they do is frequently, every month or every once in 2 months, they will visit the bridge site. They will collect some data. They will collect, do some testing and collect data, and they will analyze that. But this is happening once in a month or once in 2 months. But now, as we are talking about smart and real-time data to be required, in future we'll have a lot of bridges with lot of sensors embedded on it, and continuous monitoring of bridge is possible. Whenever there is damage, some damage occurs, we can monitor that, we can repair that at available required time, and so that we can avoid any accidents to happen. Even we are there are in MIT they have come out with tiles, smart tiles, piezo tiles. Whenever you walk on these tiles will illuminate. These are the applications. There are a lot many applications you can think of, and we can come out with many other applications. So even when I'm talking, like nowadays, recently MIT has come out with some patch or like bandage, so which they attached to the throat portion, outside throat. Whenever we do, whenever we talk, so that can be converted into useful electrical signals. So if you want more details, there like what are the groups which are working on energy harvesting? Like is something like ES Jola, which I'm working with these groups. ES Jola in Poland, they work mainly on energy harvesting. This particular project, which has $1 million project, so which they're particularly using for energy harvesting. We have NIPS laboratory in Italy. They work on this in Europe, especially in UK, Southampton University and Imperial College. So this is something APSC, SRC funded energy harvesting network. So if visit there, they have a lot of details on this. You can visit these websites. If you want, I can send you the links for these things. In US, there is something like Energy Harvesting Society. In India, IIT Madras, IIT Kanpur, IAC, NIT Tiruchi, and even in our college, we have uh, some of the basic facilities available for energy harvesting experiments, and some of the wireless sensors which we can power up using the energy harvesting are available. So before we close, we see some of the uh, videos how exactly it is done. So this video is from when I was in IIT Madras during my PhD. So this is a combination of piezoelectric plus electromagnetic energy harvesting. Like here you can see a piezo MFC attached. At the bottom you have copper coil and magnet. So it is a hybrid energy harvesting. It has both application. We have tested on bus also. You can see this scalar cantilever beam is oscillating. You can see these LED lights are illuminated because of the energy harvested from that particular system. So some of the application like we build an artificial, this you can think of as a bridge. Whenever bridge vibrates, that vibration is transferred to this harvester, and we can harvest the energy. So this is mimic vehicle movement on the pitch. So this power output, this is supplied to the, this is a sensor which measures acceleration of that particular pitch or displacement of the pitch. Regardless, we are measuring it and we are able to monitor it continuously with respect to time. Like even we are able to measure temperature of the pitch. So this sensor is working on the harvester. Similarly, the same product has been tested in a bus. Bus has some vibration. From that vibration, how much energy harvest. Even with that the vibration, that equal to power of the particular sensor. You can see some of the data come there. So next we have, you can see two videos here. One, we have particular cantilever beam. Second, cantilever beam with smaller beam. So this we can say it as metastructure. Here is the, without those smaller beams, it is possibility that large amplitude. When we introduce these two, amplitude of this main beam almost zero. So with this, what we can do is we can control vibration. We can minimize the vibration of the main function. So this is beauty of metastructure. Along with that, next stage, whatever we do is the harvesting energy from will attach video paste here, and harvest energy can be harvested. So this is setup available at our college. This is electrodynamic shaker. We can give the vibration input. Okay, what we are doing right now, we have some around 50 lakh funding for this particular project, and we are working on it. And we have collaboration with many of the IITs and other universities in Europe. So what actually we need, like if you're interested, where you can work. Actually, this is not just a mechanical or electrical work. So it is an interdisciplinary approach. We need a lot of things, like in this, when it comes to design, we need a lot of mechanical knowledge. So what is resonance frequency, frequency band, amplitude, all those things. Once you enter into IoT, we need a lot of electrical knowledge, a lot of knowledge about sensors, and to process a lot of them. We'll be having a lot of data in hand. Process that data and come to a conclusion or prediction, we'll be needing knowledge of AI. So these are the challenges that we need to address. If anybody is interested, they can think of it. So mainly now there are two sources, as I discussed, thermal and vibration. So vibration has bigger application because of its convenience. So that, as I said, like we cannot say thermal is good or vibration is which harvesting method is good. It again, it depends on the situation. So these are collaborators because of which today's presentation was possible. Maybe my guide Farooq Ali from IIT Madras, my collaborators from Swansea University UK, Friswell and Professor Alikari from UK, Litak from Blueplane, Abdul Kafi from USA. These are my collaborators and my PhD students made it possible. So thank you. If you have any questions, I can answer the question. If you have questions later also, you can note down the mail ID and you can send me or just drop me a mail. So I will try to provide you the answer.
Any questions from audience participants? ಸರ್, ಯಾವುದೇ ತರದ ಕ್ವಶನ್ಸ್ ಮಕ್ಕಳುಗಳು ಕಳಿಸಿಲ್ಲ. ಕಳಿಸಿದ ಅಂತ ನಂತರದಲ್ಲಿ ತಮಗೆ ಇಮೇಲ್ ಮುಖಾಂತರ ಕಳಿಸಿ ನಾವು ಉತ್ತರಗಳನ್ನ ತಗೋವಂತ ಕೆಲಸನ ಮಾಡ್ತೀವಿ ಸರ್. ಧನ್ಯವಾದಗಳು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಥ್ಯಾಂಕ್ ಯು.
ತಾವು ಕೊಟ್ಟಂತ ಎನರ್ಜಿ ಹಾರ್ವೆಸ್ಟಿಂಗ್ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮ ಮಕ್ಕಳಿಗೆ ಭಾರಿ ಸರಾಗವಾಗಿ, ಸುಲಲಿತವಾಗಿ ಮತ್ತು ಸರಳವಾಗಿ ಮಕ್ಕಳಿಗೆ, ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ತಲುಪಿಸುವಲ್ಲಿ ಯಶಸ್ವಿಯಾಗಿದ್ದೀರಿ ಎಂದು ಹೇಳುತ್ತಾ ತಮಗೆ ಧನ್ಯವಾದಗಳನ್ನು KST ವತಿಯಿಂದ ಮತ್ತು ನನ್ನ ವೈಯಕ್ತಿಕವಾಗಿ ತಿಳಿಸಿದ್ದೇನೆ ಸರ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್.
ಅದೇ ರೀತಿ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಗಲಿರುಳು ಶ್ರಮಿಸುತ್ತಿರುವ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳಾದಂತ ರಮೇಶ್ ಸರ್ಗೂ ಕೂಡ ನನ್ನ ಧನ್ಯವಾದಗಳು ಸರ್. ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿ ಅಧ್ಯಕ್ಷರಾದಂತ ಅಯ್ಯಪ್ಪನ್ ಸರ್ಗೂ ಕೂಡ ನನ್ನ ಧನ್ಯವಾದಗಳನ್ನು ತಿಳಿಸುತ್ತಾ ನನ್ನ ಸಹೋದ್ಯೋಗಿಗಳು ಹಾಗೂ ತಾಂತ್ರಿಕ ಸಿಬ್ಬಂದಿಗಳು ಹಾಗೂ ಇನ್ನಿತರ ಎಲ್ಲ ಹಾಜರಿದ್ದಂತಹ ವಿದ್ಯಾರ್ಥಿಗಳು ಕೂಡ ನನ್ನ ಧನ್ಯವಾದಗಳನ್ನು ತಿಳಿಸುತ್ತಿದ್ದೇನೆ ಸರ್. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್.
ಓಕೆ ಸರ್. ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಒಂದು ಸೂಚನೆ. ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಡಾಕ್ಟರ್ ಚಂದ್ರಶೇಖರ್ ಶೆಟ್ಟಿ ಅವರು ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ವಿದ್ಯಾರ್ಥಿಗಳು ಇನ್ನೂ ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಹಾಜರಾಗಿ ಈ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಕೇಳಬೇಕೆಂದು ಮತ್ತೊಮ್ಮೆ ಸೂಚಿಸುತ್ತಾ, ಹಾಗೂ ಬೈಜೂಸ್ನವರು ಕಡ್ಡಾಯವಾಗಿ ಹಾಜರಾಗುತ್ತಿರುವ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಉಚಿತ ತರಬೇತಿ ಕಾರ್ಯಾಗಾರವನ್ನು ಹಮ್ಮಿಕೊಂಡಿರುವುದರಿಂದ ತಾವುಗಳು ತಪ್ಪದೆ ಹಾಜರಾಗಬೇಕೆಂದು ಮತ್ತೊಮ್ಮೆ ತಮ್ಮ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಎಲ್ಲರಿಗೂ ಧನ್ಯವಾದಗಳು.